Hi, this paper is about the rational agent benchmark for data visualization. I'm Yifan. This is my joint work with Ziyang, Michaelis, Jason, and Jessica at Northwestern University. So our paper is about benchmarking a visualization experiment. So let's think about a visualization research experiment. Imagine we pick a paper published in a journal or conference, which compares visualization for showing the distribution of daily low temperature. So there are three visualization strategies for comparison. The mean with showing the mean of the daily low temperature with the confidence interval, showing the mean with gradient, or showing the hypothetical outcome plots. So um, the participants in this experiment are given a task. So they are going to determine the weather is freezing or not freezing, and accordingly decide whether to salt a parking lot or not to salt a parking lot. So the visualization strategies are compared by the participants' score on this task. So the experimenter set up some method to judge good or bad response and have a score associated with each participant's action and the state of freezing or not freezing. And here is the score. So this score is telling the participants a good decision is to not to sell the parking lot and the weather is not freezing, or to sell the parking lot and the weather is freezing, and they get a score of 100. And a bad action is not to sell the parking lot and the weather is freezing, and they get a score of 0. So a middle action is to sell the parking lot, but the weather is not freezing. They get a 90. So the visualization strategies are compared by the average payoff of participants on this decision task. So notice that this is not accuracy. This is the payoff that can translate to real payments after experiments. So this plot shows the average score for these three visualization strategies. And we can see tops are better because they achieve the highest average payoff for participants. But the question is, how better are they? This question remains unclear because from the plot, we only know hops are around 1 higher than like the lowest gradient. But we don't know in what scale should this difference be evaluated. To understand this question, let's see, suppose I tell you this is this is the situation with the experiment where um, the participants can actually get a highest score of 1,000, and some lower bound of participants' performance is around 20. So now the difference of 1 is only a 0.1% in total scale. So I guess the audience would agree that all realizations are bad because they are very far away from upper bound. But now let's suppose this is the situation where the upper bound is 100 and the lower bound is around 0. So now the difference of 1 is 1% in total scale. And I think the conclusion is all visualization strategies are very good because they are achieving over 90% of upper bound compared to this total scale. And I guess the experimenter just doesn't care which of the visualization strategy is used because they are all helping participants make very good decisions. But this is the actual situation in this experiment. So in this experiment, the upper bound for performance is something around 94, and the lower bound is something around 92. So in this case, the difference seems very important because this difference of 1 is a 50% in total scale. So that is saying just by using the hop realization strategy, this can help participants gain 50% more in the total scale possible. So the main message from this example is it's important to be able to interpret the results of experiments. So in our paper, we give a method to have the upper bound and lower bound and also help us interpret experiment results. So the problem is the scale for judging the difference is critical. So we answer this question by asking the question, what's the value of visualization strategies? What's the scale that we should care about? So visualization as information, they have a value in helping people making better decisions. So we provide a framework to quantify this value of visualization given any visualization experiment design. Pre-experimentally, by using our framework, the experimenter can get expectation of what is achievable in this experiment. For example, the upper bound and lower bound. And post-experimentally, our framework can help the experimenter understand the data. So our framework do this comparison between the ideal world with a rational agent, with a hypothetical rational agent, and the real world experiment with real participants as behavioral agents. So by looking at the performance of rational agents, we get the upper bound and the lower bound for the average payoff for behavioral agents who make non-optimal decisions. So for the upper bound, we designed a rational upper bound, which is the rational agent with information in visualization. So this is the best possible payoff for any behavioral agent. And for this weather forecasting example, the upper bound is around 94. And for lower bound, we design the rational lower bound, which is rational agent without any visualization. So that is saying the rational agent run a random trial without seeing any visualization presented to her, but only knowing experimental setup. And this is also the same as the payoff for the best fixed action across all trials. And here, this lower bound is around 92. So now by looking at the upper bound and lower bound, we get a sense of the scale for comparison. And this is the value of information in that visualization. That is the improvement in payoff by using the visualization. So the value of information is the difference between the upper bound and lower bound. And it's around 2 within the total scale of 100 payoff. So that's the main idea of our framework. So our framework is a decision theoretic based framework. To use our framework and get lower bound and upper bounds, we want first to identify the decision task. So to identify the decision task, there are 5 key elements to identify that. So the first key element is a payoff relevant state. And in the weather forecasting example, that's the temperature being freezing or not freezing. And then the data generating model, which is how in each trial that payoff relevant state is generated. For example, in that experiment, you can say the temperature T is drawn from some normal distribution where mean is fixed and standard deviation is varying across 4 different levels. So in each trial, the probability of weather being freezing is equal to the probability that this temperature is below 0. And then the agent's action space. So the agent takes action from not to salt the parking lot and salting the parking lot. And then we think of the visualization as a signal that's informing the agent about the distribution of the payoff relevant state. So this visualization transforms data into a plot that's shown to the agent, and this implies the distribution over states. For example, the mean with confidence interval is the same as telling the agent what is the standard deviation in that particular trial. So by knowing this, by seeing this mean with confidence interval, the agent is able to infer the probability of freezing in that random trial. And then a scoring rule or a payoff rule that's telling the agent what is a good or bad decision. So these score rules can be used as both incentivization that translates the payoff of participants in experiments to real money after the experiment, or evaluation that interprets the experiment results. So for example, the principal can use different scoring rules for incentivization and evaluation. Like for incentivization, just count the number of tasks the participant has finished, that is flat payment. Or for evaluation, use, for example, a quadratic scoring rule. So in our framework, the rational agent knows experimental setup and makes the optimal decision through standard utility maximization theory. And our framework is applicable to a wide range of visualization status as long as 2 conditions are satisfied. First, there are different states. That is, there is something to infer about the the payoff relevant state. So one counterexample is the exact same data is visualized so that all visualization have the same payoff relevant state, and there is no uncertainty about the state in decision problem. And another condition is there is a best response. And one counterexample is participants are asked to report something subjective like emotions. So that's our framework. So with the rational agent framework, we are able to do other things beyond upper bounds and lower bounds. So for example, we are able to quantify what's the information asymmetry between the visualization plots, visualization strategies. For example, if in addition the experimenter want to compare mean visualization to the other three visualization strategies, so this mean visualization is naturally less informative than the other three. So pre-experimentally, the experimenter cannot expect mean visualization to behave as good as the other three. And also this can help the experimenter analyze the increase in payment for rational agent by consulting the visualization. So this helps the experimenter to quantify what's the incentive in this experiment. And post-experimentally, our framework is helpful in analyzing the behavioral losses, that is the loss from the upper bound. So we separate the loss into two different sources. The first one is the belief loss, which is the behavioral agent not perceiving information in visualization. And the other one is not is optimization loss, which is the behavioral agent is not maximizing payoff given the perceived information. For example, like behavioral bias or misunderstanding of the task, they are all counted as optimization loss. So we apply our framework to two award-winning papers. One is the effect size judgment paper, which is the best paper in VIS 2020, and the other one is transit decision-making paper in CHI 2018. And these two papers are known for their rigorous experiment design and analysis. So by applying our framework, we still have new findings to these two papers. And we identify ways to further improve design, and also we identify previously unrecognized sources of loss in performance. So to conclude, we provide a framework to quantify the value of visualization given a visualization experiment design. And by applying our framework, we can identify the experimenter can improve decision experiment designs, and also to improve the knowledge gained from observed behavioral performance.